Okay, in this presentation we will look at the Weibull distribution. Okay, so the Weibull distribution is commonly used in engineering and industrial applications. Okay, so the Weibull distribution can be used to analyze the reliability and lifetime of components in various engineering and scientific applications. By understanding the median and interval probabilities, engineers can make informed decisions about maintenance, replacement, and risk assessment. Okay. So here's our question. A certain type of electronic component has a lifetime that follows a Weibull distribution with a shape parameter alpha equal 1.5 and a scale parameter beta equal to 1000 hours. So we have two exercises here, A and B. So exercise A is find the median lifetime of the component, and exercise B, calculate the probability that a component will fail between 800 and 1200 hours. Okay, little glitch there, never mind that. So the median lifetime, TM, is the time at which 50% of the components will have failed by. Okay, so how do we approach this? So this is the standard approach for all types of calculation where you have to derive the median. So you get the cumulative distribution function, f of t, and solve it by letting that equal to, letting the expression equal to 0.5. Okay. So here we have f of tm is equal to 1 minus the exponential of minus tm divided by beta to the power of alpha. Okay, so what we're going to do is let that cumulative distribution function equal 0.5 and solve for tm. So solving for tm and rearranging. So first off, what we will do is just rearrange it algebraically. So we have the exponential of minus tm divided by beta to the power of alpha equals 0.5. So essentially just remove that 1 minus and just rearrange it a little bit. So now we're going to get the logarithm of both sides. Okay, so when we get the logarithm of an exponential function, essentially we end up with the argument of the exponential function. So the logarithm of the exponential of minus tm divided by beta to the power of alpha is simply minus tm divided by beta to the power of alpha. Okay, and we have to get the logarithm of both sides, so we end up with the logarithm of 0.5. Just as a remark, it's evident that it's absolutely necessary to know all of the rules of logarithms, exponentials, and power rules, etc., as they are absolutely fundamental to coping with these mathematical problems. Okay, so just remember to have them fresh in your mind. So just moving on here, we have t over m to the power of alpha divided by beta to the power of alpha. Essentially, I've just rearranged the previous expression. I just rephrased it basically and negated both sides. So that is equal to minus the log of 0.5. Now minus the log of 0.5 is actually log 2. Okay, so the expression becomes tm equals beta times the logarithm of 2 to the power of 1 minus alpha. Okay, so using the parameter values that we were given at the start, t of m equals 1000 times log of 2 to the power of 1 over 1.5. Okay, so beta equals 1000, alpha equals 1.5. So you have 1000 times the log of 2, which is 0.6931, to the power of 2/3, and that works out to be approximately 783.22 hours. Excellent. So the second question, calculate the probability of failure between 800 and 1200 hours. Essentially what we use here is a cumulative distribution function, which we've used already, but now we're just going to use it again. And to calculate that interval probability, essentially what we do is subtract from the cumulative distribution function of the upper bound, which is the cumulative distribution function of 1200, we subtract the cumulative distribution function of the lower bound of the interval, which is 800. So f of 1000 minus f of 800. Okay, so using the cumulative distribution functions there, we have that expression there. 1 minus the exponential of 1 minus the exponential of minus 1200 divided by 1000 to the power of 1.5 minus 1 minus the exponential of minus 800 divided by 1000 to the power of 1.5. So essentially we can tidy that up. and rearrange it. So we have the exponential of minus 800 divided by 1000 to the power of 1.5 minus the exponential of minus 1200 divided by 1000 to the power of 1.5. And really I could have gone 0.8 and 1.2 there, but just to sort of make sure that you can keep track of it. So this is a bit of calculator work. We have the exponential of minus 0.7155 minus the exponential of minus 3145. That works out to be approximately 0.4889 minus 0.2686. So that works out to be 0.2203. So to sum up, we have the summary here. Just move on to the next page. So the median is half of the components are expected to fail before 783.22 hours, and the interval probability is that there is a 22% chance that the component will fail between 800 hours and 1200 hours. Just as a quick remark, I'm going to introduce some R programming language. This is the Weibull distribution, and this is how I might use the R programming language essentially to solve the second one. So in the first instance, we have the cumulative distribution function of 1200 using the scale parameter, the shape parameter 1.5 and the scale parameter equal to 1000. And the R function is Weibull. I do something similar there for the cumulative distribution function of 800. I'm not going to be so specific about the specifying shape and scale, because if you put it in the right sequence, it just sort of assumes it. And the difference of the two there is what our answer is, 22.03%. Okay, so we'll leave it there.